All right, cool. So yeah, what topic was it? Origins, right? So like near the beginning of the semester, I kind of like made a point to talk a little bit about trying to like introduce like an evolutionary way of thinking, which it sounds like an obnoxious thing, right? So like, how do I word this better? You have to be careful how you think about things through an evolutionary lens. Because we, as like problem solvers, the humans, like we see a problem like we want to fix it, right? And we intelligently go about doing it. So we have a bad habit of looking at like evolution working in the same way. But that really isn't how it works, right? Evolution just does its thing. And you got to think over long time periods, okay? So you have to be careful when thinking about problem solving and thinking about things through an evolutionary lens. Like you can look at how an organization is structured through a system design view, or like you might even be able to like look at it through like an evolutionary, like, well, just everything kind of like fell into place, and if they worked good, if they did not work, okay, whatever, right? So you can really start to look at problems through different lenses, and it might give you an appreciation of how we maybe like ended up where we are. And you can think about everything from an evolutionary lens. Now, if I go and I design if I go and build a robot, okay, fine, right? Like I built that robot, it was designed by me. But you can really start to look at like everything through that evolutionary lens. You could think of like we could think like, okay, biological evolution, great, fine. But you can really think about like systems being evolved, right? That could be like organizations, our economic system, countries, our culture, whatever you want, you can think about through an evolutionary lens. That doesn't mean it's going to give you like secret insight into the world or anything. It's just you can maybe start to think like, I guess how could that happen? Like even like I remember thinking like the game of like baseball, right? How the hell did we end up with the rules we have with baseball, right? Or football or anything, right? That's not like North American football, right? But baseball. Not an overly complex game, but a lot of like nuanced rules, right? And we ended up here. Like no one sat down. There wasn't a committee of people that are like, okay, here's the game we're going to play. It just started. I like to envision like people playing catch, like 1,000 years ago or maybe more, right? And then someone's like, I bet you I could catch it. And then they're like, well, I'm going to throw it harder. Well, I bet you I can whack it. And then like, how did we like go from no baseball to baseball? How did we go from no North American football to North American football? How did we get there? No one designed it. It just happened that way. In fact, if you go and look at the origins of these sports, we don't really know. Because people were playing like who invented soccer? Probably like 5 million different people. They're like, look at that, right? There you go. It just happened, right? So you can really think of everything through that lens. That's really what I want to get here. And you might think like, okay, what could you really like achieve with evolution? Well, look, this stupid system. This isn't evolutionary computation. It's dumber than evolutionary computation, okay? It's just this system of rules. Remember this linear, singular, one-dimensional automata, right? Based on these simple rules, you can get quite crazy behavior. You can get some really interesting, like emergent properties. All right? And then there was Conway's game of life, which is even more wild, right? We saw that you can make Conway's game of life in Conway's game of life, which means you can make Conway's game of life and Conway's game of life and you can do this forever, recursively, right? Like it just goes on forever, which is kind of wild if you kind of think about like the implications of such a system. And is Conway's game of life complex? No. I mean, it's complex in the sense that like the emergent properties and what comes out of it is complex, right? But in terms of like the rules that you follow, hilariously simple. And yet, such crazy complexity comes out of these simple rules. And I think I brought this up at the beginning of the semester. For me, when I was younger, I remember like being really into like the most sophisticated complex board games. You know what I mean, right? Some of those like crazy fun board games, right? But as I've gotten older, I just don't have the energy for that anymore, you know? But what I really like is that doesn't mean I don't like depth. It doesn't mean I don't like complexity, but I don't like complexity for the sake of complexity. Like think of chess. You don't have to be a chess expert. Chess, not an overly complex set of rules. The hardest part is remember all the moves. Once you know that, whatever, that's just the game, right? But think of the immense complexity of chess. It doesn't come from the rules, it comes from like the application of those rules. That's where things are interesting. And we did talk a little bit about like the invisible hand, right? And how we got to be careful. As far as we know, there's no omnipotent force guiding our economic system, right? There's not. It just happens. And yet, here we are. No one person knows how to make a pencil. And yet, here we are. How did this happen, right? Well, that's where like this idea of like emergence comes from. And what's really tricky about emergence is like definitively you will never be able to know it's going to exist. Like what do I mean, right? Like I can't look at something and be like, wow, look at like, because of like the sum of the parts, I will observe emergence. Like that doesn't happen. You can, like for example, this might not be the best example, but let's use this as an example, right? Like, oh, when is AI going to be like conscious or something, right? Like, oh, well, when's it going to be conscious? And then there's people, well, you know, we know how it works, so we know it's not, we know like it's not conscious, right? Like we know how it works to a degree, so how could it be there? But here's the funny thing about emergence is you wouldn't be able to tell, just because you know how something works doesn't mean that you can determine, oh, yeah, oh, that's sufficient for like consciousness. Like, no, that's not possible. You would never know. In the same way, like I could never know, are any of you in here conscious? I don't know. I am. Are you? Right? How do I know? Well, by my interface, like I can only tell based on like my and our shared experiences, I suppose, right? But like you can never know it's there by looking at like the underlying mechanics. You kind of have to look at like the box as a whole, and then is it really there? I don't know. All right, so emergence is a kind of a funny thing. We all can kind of tell when like emergent behavior exists, like our economic system, like, okay, all this extra crap is going, oh, fantastic, right? Like there's like some amount of like coordination despite no coordination. But yeah, it's kind of tricky like that, right? Because it's like necessarily like greater than the sum of its parts, let's say, for lack of a better term. I'm sure there's a much more elegant way to describe what I'm trying to say right now. I'm not equipped for it. Anyways, all of this is to say, hopefully now you can see how like, well, with evolutionary computation, how do things change? How do we apply these rules and whatnot? That's like, there's more, we've added more complexity than like these simple things, and we're able to get interesting things, right? I suppose really what I'm saying is I think you could probably like, it's probably pretty valuable to spend time thinking about things from that, like that evolutionary lens, I think. I think you could probably gain a lot of insights. Anyways, any questions about that? Is your hand up or are you just sitting? You're just chilling. All right, cool. So, last time, let's see. Okay, I'm going to describe PSO, okay? So I'm going to go through this and describe an implementation of PSO. And like I was saying last time or the time before, the last assignment is going to be PSO. And I'm pretty sure the assignment is go find one of these functions and just make it work. Okay, so this would be really good. Maybe tomorrow we do like an actual, or Wednesday we do like we implement, I don't know, whatever, I'll figure something out. Anyways, PSO. I'm going to show a working implementation of PSO. I believe I showed you last time, but I just kind of copy and pasted it and ran it and said, oh, there you go. But let's take our time. It's a simple implementation that incorporates no particular enhancements, and that's fine. So like on your assignments, add enhancements. And like we were talking last time, a lot of those enhancements are pretty straightforward, like binding things, right? The problem PSO is being applied to is some arbitrary mathematical benchmark function, okay, for real number optimization. And despite how simple the implementation is, you'll see how well it performs. Well, acknowledging that we're dealing with real numbers, so how precise can we be, right? All right, PSO is often used for real floating point numbers. And again, I probably said this again, I just want to make sure I'm clear. When I'm saying like ideally real numbers, but we're in computers, so they're floating point, right? Any real number optimization problem would be fine. There's a lot of benchmarks out there. Here's a Wikipedia page about a bunch of benchmarks. This is, no, not that one. This one. This is the one I used. Why? I don't know. I liked it. Something about the way it looked just drew me in. I don't know. But it was entirely arbitrary, okay? But a bunch. This one here, Ackley function, that's a really popular one. And I believe it's popular. In fact, this is a really popular one, by the way. Why I didn't pick it, I don't know. I probably didn't pick it because I wanted to be different. But I picked it a few years ago. Anyways, the goal is, given some n-dimensional floating point number function, the function takes n real numbers as arguments, and it returns a single value representing like, well, what is the output of that function? And the goal is, I want to find the smallest value, or biggest, whatever, whether I'm minimizing or maximizing, whatever. So what are the arguments? What inputs to the function gives me the smallest output, or largest, okay? That's the goal. If you're thinking, like, how do I tie this to a real problem? Anything you want to optimize where you're trying to find like real, like when you're dealing with real numbers, you can use this, right? This function is a stand-in, this benchmark function is just a stand-in for some real number optimization problem. Find the arguments, okay, depends on if it's minimizing or maximizing, right? So here's one, the Matthias function, I don't know. Here it is. Again, why did I pick it? I don't remember, but here it is. Where did it come from? I don't know, ask Matthias, I don't know. But it's a function, takes two arguments, 0.26 times x squared plus y squared minus 0.48 xy, right? Cool. The function was arbitrarily selected. The output values for the function, the optimal values happen to be 0, 0, by the way, okay? Great. So there we go. So here is a two-dimensional plot, but it's trying to convey 3 dimensions. I believe, like, this is a relatively convex search space too, so it's going to be pretty easy for PSO to handle. Let me explain. So here's x and y, right? So I want to find the point on here for x, y, and if you look over here, this is where it's trying to show you that third dimension, all right? And you can still kind of see here because it's trying to do like topographical look, but more yellow is higher, more out of the page, and more dark blue is lower end of the page. So you can see here that as we go towards the center, it's going down. And it's not like a perfect circle, it's like an elliptical shape, whatever, all right? Now, when I said it was convex, concave? One of those words. Concave, right? Yeah. What I mean is, if I were to just throw a bunch of marbles on here, it would kind of want to just go down there anyways, right? So we could probably use a simple hill climbing algorithm, or here, hill descending algorithm to find the minimum. So when you have problems like that, any optimization algorithm is probably going to do pretty well. So whatever, maybe not the best benchmark problem to demonstrate PSO's effectiveness. Something like Ackley could be better, but again, it doesn't matter. It's just optimizing something here, all right? All right, here's the function. It's okay, the matches function is used as a minimization problem, takes 2 arguments. The goal is to find the values with the smallest. Okay, look, we know that it's 0, 0, but we're pretending we don't. Okay? So yeah, the point is to see, can PSO find it? So here it is. There it is. Where did this come from? Well, I just looked it up. Look, I was good and I said where I found it. Wonderful. Okay? So how do we initialize? Are all particles and their velocity starting positions I'm going to randomly generate, okay? But I'm going to start them within some bounds, right? Not really an enhancement. When I was talking about the enhancements by like binding, I meant like once you hit start, don't let it go beyond certain ranges. Kind of like setting where you want the particles to start existing. That's normal, right? I don't remember what I set it as, but how are we going to do it? Well, okay, for example, okay, however, So how am I initializing it? Randomly. You could do whatever you want to initialize it, kind of like a GA, right, or evolutionary computation, basic ones. All you need to do is just start with a bunch of positions. You got to be careful, though, because, yes, if there's something about the problem that I know where I could be like, look, I already know like reasonably good solutions are going to be like here in the space. Yes, I can seed my initial set of particles around what I know is already good, and that will probably help the search, but you always got to be careful of biasing your search too much, because if I add too much pre-existing knowledge, it could kind of like maybe set the algorithm to go the wrong way. Because you always have to admit, I'm only using these crazy, wild computational intelligence algorithms if you don't know what you're going to do. So as soon as you start to apply more knowledge, you're going to bias it. The whole point of these algorithms is that it like thinks outside the box and it goes its own way, right? So, you know, always be a little bit careful. Is that clear? I want to make sure it's clear. Like here's a bunch of good TSP implementations. Great. Don't be surprised if your evolutionary algorithm doesn't get out of that local optimum, right? Similarly here. So how are we going to do it? Any way you want to do it works. Here's how I did it. Start with an empty list of particles. I'm going to keep appending individual particles to that. That's going to be my set of particles. I don't care, for whatever in range of the number of particles, some hyperparameter I set. So maybe it's 100, maybe it's 10, maybe it's 1,000. Doesn't matter. I'm going to create a particle. It's going to be a dictionary. Position, I'm going to start by getting an NP random uniform distribution. I guess I could have done Gaussian, but I'm picking a uniform distribution of value, picking from a uniform distribution of values between the lower bounds and high bounds. All right? What are these? I don't know, maybe -10 and 10. I don't remember what I set it as. And what's neat about this one here, it's got another argument that I can give it. If I say 2, it doesn't just give me back one number, it gives me back like a pair. Cool? Cool. Because I need x and y, so its position needs to be an x and y pair, so I put in like 2. This is the number of dimensions the problem has. Is that clear? So position at the end of the day will be, looks like, a NumPy array of length 2, representing its x, y position. All right? Velocity, same idea, right? Except instead of being bound by the positions, we bind by the velocity starting values. Again, I don't remember what these were set at, but it doesn't really matter, right? So I've got 2 things here, position, velocity. You'll notice that, like, I think I said this last time. Yes, I could have made like a class, and each particle could be an object, and the object could have like 3 fields, right? Its position, its velocity, and its best known position. I could do that, but if you just have like a data class, make it a dictionary, right? That's, you know, there you go, right? Clearly it's better. Particle, best known position, just take some whatever, its starting position. It doesn't really matter to me, okay? And then append it to the particles. And then for here, the global best. You know, I look at this and I think like, well, maybe I could set the global best to something in particular. But you'll see that once we start the algorithm, this gets updated anyways, so you'll see. So I just said like, I don't know, just some whatever. The 0th particle's position's the best I've seen so far. But this really just means like it's undefined at this stage, okay? To starting position, randomly selected, they are bounded. Oh yeah, perfect, there you go. -10, nailed it. -10 and 10. its velocity starts there. 10 particles, 100 iterations. I set those values, number of dimensions. Cool. There you go. Most of these I just set based on, well, this is kind of bound to the function that I'm optimizing. These I just picked, I don't know, number of particles. These are relatively small. I just picked them for demonstration purposes. And these were the values we talked about last time. That, what was the guy's name? Anyone remember? Do I say? Vandenberg. There you go. You could have impressed me by saying Vandenberg. But that guy picked. Great. And here's his thesis, I think. Look at that. Consult the thesis. Don't ask me. Ask him. 2006. Wow. That's a long time ago. All right. Okay, the numbers of dimensions is dictated by the function. The other values I just picked. They're not really arbitrary. That's kind of a lie, I suppose. They weren't arbitrary, but they weren't like meticulously set. All right? Any questions so far? Okay, I'll pause for something. All right. Evaluation. Well, this is simple. We've got the function. We have a set of particles, each with a position. We'll just pump each particle's position into the function to get its value. All right? Particle's position corresponds to the arguments in the space. Provide the particle's coordinates to the function to evaluate. Once the function value is returned, update the particle's best known position and global best position. Notice that each particle doesn't actually, like, particles don't even need to know what their fitness function is or what their like value is. All it needs to know is where was the best one. I don't even need to remember what it was. And by the way, if I'm always keeping track of the global best, when I'm done the algorithm, the global best is going to have the answer, which is pretty cool. I mean, it won't have the fitness value, but it'll have its XY pair, which if I have, I can calculate the fitness value, which is pretty neat. All right, so for particle in particles, take the function, put it in its position. We talked about this last time, right? How that basically like unpacks the iterable thing into separate arguments, because this function wants 2, particle's position has 2, but it's in one list, unpack it. So we get the particle value. If its particle value is better, less than, I guess we're minimizing, if it's better than calling the function on its best known location, then the best known position will be updated to that position. Again, I'm not even saving the particle value. I could, I guess. There's nothing stopping me from doing that. I guess it could, you know, whatever. And then down here, if the particle value is less than on the global best, basically, is the current particle's position better than any other position I've seen so far? If it is, update the global best. Done. Cool. Remember, each particle, though, doesn't know the global best. Like, in that it's like not saved in the dictionary. It can know the global best because it's saved elsewhere, but the dictionary only has the position, the velocity, and its best known position. Okay? Update velocity and speed. All right. Once the random vectors for the cognitive and social terms are determined, right, because we need like the R1 and R2. These are random vectors that we generate. Each particle's velocity is updated. I don't know what this goes to. Okay, I guess I linked back to last lecture, whatever. And with an updated velocity, we can update the position. Easy peasy. So for particles, so that means there's like, for each iteration, we have 2 for loops. We have to go over each particle and then go over each particle again to update its velocity, right? And you might want like, well, why? Couldn't we do it in the same loop? And you could, but, and it's not necessarily a bad thing, but what would happen is, like, imagine you started going through the particles and like evaluating it and updating its velocity, right? And then like halfway through, we find a new global best, which would change the trajectory of like half of the set of particles. So when you do like 2 things, one after the other, you could kind of think like, as far as the second loop is concerned, the particles finding out like, do they have a new global best and do they have a new best? That you could think of like, oh, the order of them didn't matter. So as far as I'm concerned, it happened instantaneously. So now I can iterate over it, whatever, it doesn't matter. All right, so what's going on here? Well, I get the two random vectors, R1 and R2. And by the way, this works really well because we're using NumPy, right? Because with NumPy, when you do like multiply and add, it's going to do like vector-based stuff, right? If we were to do it with lists, we could still do it pretty easily, but we'd have to add some extra like functions and whatnot to do it. I'm making use of NumPy because it makes like the math really straightforward. Okay, so we get the two random vectors. Then the particle's velocity is going to be set to the inertial times the particle's velocity, right? Inertia, particle's current velocity. Cognitive times R1 times the difference, particle's best known position minus its position, right? And plus the social, R2, global minus its position. So that's updating the velocity. No crazy hidden math here. There it is. Okay, it's a weighted sum. Then update the position. Well, you just add two vectors together. Its velocity plus its position will give you its new position. Vector math, yay, right? Pretty neat. So now this is how the particles move. And then that's it. We just keep repeating that process over and over and over. The particles move. How are they now? Particles move. How are they now? And so on and so on and so on and so on. And then when do we end? Whenever we want. Here I just have like some number of iterations. Same thing goes as the regular GAs. Has it converged? Have we seen no updates in a while? Has it passed some specific threshold? Some number of iterations? Whatever you want, you can use. And then when we're done, because again, we never store the actual best value, and often, like, okay, what do we want, right? Like, think of TSP. When you're done, you want the Hamiltonian path, right? Yeah, sure, you want to know the total distance, great, right? But really what you were looking for was the Hamiltonian path, right? So that's what like the global best would be. It would be that XY pair. That's what I was looking for. Oh, and like, oh, and this is what its fitness was, its output was. All right? And there we go. So we have to still calculate it one last time because the global best stores that position. But what is it? Well, just calculate it. Pretty simple to calculate. Any questions about that PSO? All right, so real quickly, let's go. Looks like, okay, I downloaded it. Notepad, sure. So here we go. I hit run. It's pretty quick, right? There. Maybe I can fit it better, right? So the best position I found was there. All right? Pretty darn close to 0. Okay? Let's run it again. Oh, there we go. Look at that. We got even closer. But this is one of the, like, you can't look at this and be like, oh, the answer was 0. It was wrong. Look. Remember, we're dealing with real numbers. How many numbers are there between negative 4.9 times 10 to the negative 5? How many numbers are there between that and 0? An infinite, right? Like, we could play this game forever. I look at that and be like, okay, yeah, that's good. So you got to be careful when dealing with real number things. Don't let the precision get in your way of understanding that, like, oh, no, this is a good result. All right? Now, for fun, let's go and, because why not? We got plenty of time. Let's go and do the Ackley function. Ugh. Okay. All right. I'm guessing that's like E, right? EXP, that's probably E, right? Yeah? Yeah. All right, so let's try to get this implemented. No, here, we've got to go this way. Nope. What is that rumbling? Does everyone else hear and feel it? Only one other person in here? 2 people? Raise your hand if you don't know what I'm talking about. You don't hear that? No. Maybe that's what's... There's like a low... I'm guessing there's like a giant truck outside or something that's like vibrating. Do you hear it? There's the... That makes perfect... It's probably the construction that's taking place. Literally right there. That makes sense. Okay. Let's start doing... Okay, am I spelling it right? ACKLEY function. X, Y. All right, this is a bit of a doozy. So, negative 20 times np dot e xp, probably that, right? I'm doing np because it's already imported. Negative 2 times np dot sq square root. Stop hopping up. No. Stop it. The square root of 0.5 times x squared plus y squared. So that closes the square root, yeah. And that closes there, yeah, okay. Minus np.exp of 0.5 times, my goodness. Okay. Here, I'll just do this temporarily. Oof. 0.5 times np.cos of 2 times np.pi. Is anyone else immensely bothered by the fact that pi is not in like capital I, capital P, capital I? Oh no, it's lowercase p, lowercase I. Yeah, I know, I just hate that it's a constant. It should be uppercase, right? Come on. All right? I don't know about you, I ain't changing that number. Times x plus np.cos of 2 times np.pi times y. Oh my gosh. Okay, that closes, that closes. No, I didn't do, okay, there. And then that. And then that's to the exponent. Right? Plus e plus 20. Plus np dot e plus 20. All right, yeah? Does that look, am I right? Here, I'm gonna rely on you. Oh my gosh. I need all of y'all's set of eyes. Is that right? Oh, it's not. 0.2. Is that what you were seeing? Yeah.
Just go through it slowly.
Yeah. I really hope this isn't nested. Yeah. Yeah, I'm seeing nods. People are still, I see, okay, I'll give you a sec. All right, well, let's, if we can find a reasonable answer, here's hoping it's right. If we get wild results, could be wrong. All right, so now all I got to do is go here, switch out. I don't want that. I don't want that. I don't want that. And, of course, down here as well. There. Cool. All right, I've replaced it. Now, why am I changing it to the Ackley function? Well, I talked about this a moment ago, but we can go back just to make sure the point is clear. This right here. So you can kind of see that this is like going to be tricky. It's convex or concave, right? In that, like, as you go towards the center, right, we're going there. But you can see there are a lot of local minimum for these particles to get stuck in. Okay? You see what I mean? They're going to go here, and it's always going to be worse to go from here to here. So it's going to kind of be like pulled into here. Like, in a situation like this, think of like a mattress with a bunch of like bowling balls. A really big bowling ball in the center, and then more kind of like throughout. And if you dumped a bunch of balls on it, they're not all going to go to the center. They're going to get stuck in the little indentations. Do you see what, you know what I mean? So this should be far more difficult for the algorithm. Oh, and it did say the bounds were -5 and 5. If I remember correctly. Yeah, -5 and 5. So I just set those values. I don't know how much it would have mattered, but I'll just listen to what it's saying here. All right, so what do we think? Are we going to get a result close to 0? No. Well, actually, what is? Yeah, f of 0, 0 is 0 here. Look at that. Is it 0? Because I'm getting results really close to 0, though. But it's saying it's -19, but it's saying f of 0 is 0. Am I crazy? Well, let's check. I must have my calculation wrong then, right? We're still fine. Yeah?
Is it something to do with the plus 20 in the function? Because that should cancel out the -19.
Yeah. So I guess the multi-line thing, I did something wrong. I think I need backslashes or something for it to work right. There, look at that. So there we go. It's actually working pretty well. Darn, I was hoping to find one that was actually pretty tricky, and I was hoping we'd have to kind of like tune these arguments. Let's see what happens if we start with the different bounds. Like, what if we do like -50 to +50? I wonder if that's going to make it really hard. Not really, no.
Almost made it better.
It almost made it better. Now, what would be really cool is if I kind of like generated like a visualization, kind of seeing where the particles were going over time. That would be really nice. But again, look at that. Great. Man, I'm kind of disappointed. I was hoping for something crazy. What is this one here? What is that? D. What is D? D? Oh, interesting. So it's showing, what is D though? It's kind of showing that these are actually variable, but these are the recommended like plug-in values. Although, again, I don't know what D is. A, B, C. Well, whatever. Has anyone noticed?
D's dimensions.
Is it? Does it say?
It's up higher in that.
It does. Okay, where D is the number of. Yes. Okay, for D. All right. I was about to be really mean, but lately I've noticed Wikipedia. Has anyone noticed Wikipedia is not as great as you want it to be lately? Lately, I don't know. Lately, I've been really mad at Wikipedia. Has anyone else felt the same way?
Are you donating?
I did years ago. And when I donated, it said if you donate once, we'll never bother you again. That was a fucking lie.
No, they bothered.
Of course. You know why? Because someone who donates once will probably donate again, right? So like, I don't know, it was a lie. And it was like when I bought like the app back in like 2008 or something, or whatever year that was. Yeah, that was a lie. Whatever. If we go here, by the way, there's also this nice data set where optimization test functions, in addition to like what they had for on the Wikipedia page, there's this one from like Simon Fraser University, which is pretty cool. A bunch of other functions as well. And they've got some nice 3D visualizations. So like here's the Ackley function, for example, kind of plotted in 3D, so you don't have to kind of like use your imagination. And what I like about this one is unlike like the plus 20, you can really see here, right? And to me, this helps visualize like how stark that is, right? How like, oh wow, no, there's a huge difference between here and here. And if we go back, like what else? This one, cool, looks good. Ooh, look at that. Someone should go, oh, here we go. I could probably copy this. Oh, man. Why not like R? Stop it, sheesh. Should email this guy. Just please have copyable regular code. Whatever. If it was simple, we could easily switch these out and kind of see. I was really hoping I could find one that would be tricky. I don't know. Let's see. What else we got here?
Those are definitely stats plots.
Yeah. I bet you this guy's a statistician. Let's see. Who is this guy? Virtual library. I'm sure this guy is a champ. Derek. I can't copy that. This is annoying. It's not Derek, though, which I love. This is clearly this guy's this guy's like website, but he's like, hey, if you got any problems, ask this guy, which is funny. It is, but I'm really lazy because I couldn't copy it. SFU. Or maybe this was a student, and the other person was there. Okay. Sonia.
Funded by insert.
No, it was a student. Glaciology. I don't know. That's crazy. I don't know what they were doing, but good for them.
Do the de Jong function.
The which one?
De Jong function. Steep ridges and rocks.
Where?
That one.
Oh, yeah, that'd be a good one. There's no, okay, this one hopefully is,
Hard.
this one hopefully is quite clear why, like, okay, you're never getting out of those. Yeah. All right. Any last questions? All right. I'll think of something for next time. I'm guessing maybe next time, I don't know, we just kind of like hack around with PSO for a little bit. Who knows how long it'll be. And then after that, I'll start to think of other things to do to hold us over until what I'm very much looking forward to, the 5th for his lecture, which will be lovely. All right. I'll see you all later.